we've already talked about that, so I'm going to can that one. Okay. And I think I'll go on and can this one. And I should have done this before. Sorry about this. This will take just a couple of minutes. I knew there was something else I had to do. Well, I thought it would be just a couple of minutes. Oh, here it comes finally. Okay. Okay. All right. While I'm waiting for that to come up, let's continue. Okay, let's talk about the other two issues of safety. We covered fire. Listen to that. What other two things, safety issues, do we need to concern ourselves with? Yeah. Two safety issues. We talked about fire last time, right? And we finished it. You can hear that on YouTube video when I did it. What other two safety issues do we need to think about? Tornado. Tornado. Okay, I'm sorry. I didn't hear what you said. All right. Okay. Is it missed? Yes, sir. Okay, good deal. Still learning names and faces so much. I have a really good memory, but it's short. Okay, so I have trouble with that. Okay. So what if, let's just classify weather emergencies. So you hear the alarm goes off, and you can hear it really well from here. What do we do? What do we do? Go downstairs. We go low and interior. Keep that in mind, low and interior. So how do we get there from here? All right, here we are in the corner classroom right here. Okay, we go out the door here, hang a left, go down that little half line of stairs right there, and then immediately at the bottom, hang another left, go down one more flight, and then at the bottom, you come out on the lowest level of the first floor, low as you can go. Now, not quite as low as you can go, but close to it. Right in front of you are the restrooms when you come off the stairway. And now the first floor, it looks sort of like this, but a little bit different. So, actually the restrooms are not a bad place to be. Why? The walls are close together, and you got lots of corners in there. That's where the strength of the building is. Especially this back wall back here. Now, I don't know if you've been around the building enough to know, even though when you go down this half flight of stairs, you're still on the second floor here. There's the floor beneath you. But if you go through this corridor without going up or down a single step, you're on the first floor. That's where financial services, records office, all that stuff. Yes, those double doors. Yeah, those double doors. So if you go from second floor to first floor, when you pass through those double doors, okay? So that means that's as low as you can go here, but you can go down lower. What does that really mean? Underneath this is soil, structural material, okay? So therefore, the back wall back here on the first floor, down that lower first floor, that's as safe as you can be because there's nothing to make you collapse on. I mean, you'll fall off. Yeah. So that is a safe wall back there, okay? So the walls are good, corners are even better, and that back wall is great. Now, if you don't want to spend the next couple of hours in the restroom, which I can understand, the very next thing, you're actually 2 more steps down, and you get to a little office there. It's the academic dean's office. Now, she's seldom over here. She was over here both Monday and Tuesday of this week, but she probably won't be here much. I think she's coming over to help with the help desk one day. But most of the time, when the term gets going, she's mostly on the Birmingham campus. But she is over here occasionally. Or other people may be using that office. And if it's unlocked and they invite you in, that's a pretty safe place. Why? Close walls, lots of corners. Okay? So that's good strength there. But it's usually locked. So you can go on down the hall here, there's a classroom. It's 160. Now it's not like this, but it's similar. It doesn't have a door here, but it does have a door down there. Now that's okay. Especially this back wall is great. And the corners are great. The rest of it, you don't want to be in the middle of the room. Okay? Because if something does collapse to that wall, and the corners are best. That wall's next best, even the other wall is good too. So you could go in there if you wanted to. Then you have a glass door here that goes into the library. And immediately in the library, immediately to your right, is a little computer lab. Smaller than this, so therefore the walls are a little closer together, and you got the four corners. Not a bad place to be, especially that back wall. Okay? Right next to that is a room I call the reference room. Okay? It's a little bit bigger, but that back wall is great, and the corners are pretty good. The only bad thing about that, they do have bookshelves there. I guess if the building started rocking and rolling, they could fall on you, so you might want to. But don't go any further, because any further in the library, you're going to be on the outside. You want to stay interior. Now, I left off the space that probably most people will actually choose to be, and that's the hallway. The good news about the hallway, the walls are relatively close together. The only bad thing about the hallway is no corners. But the other really good thing about the hallway that none of those other spaces have is the fact it has emergency lighting. And there's a real good chance if there is a real serious weather emergency, we're going to lose power. And if we lose power, the restrooms are totally dark. All those interior rooms are totally black, you know. So the hallway has emergency lighting. Unless you really want to go and take a nap somewhere against the wall, you might want to consider staying in the hallway. But you have choices. All right, here's Catherine. And here's Jordan. Good deal. We're only missing Daniel Granville. Okay. All right. And we increased the class size by one. That is good to happen always. Okay. So that's what we do. And you stay together. Okay? If you go, oh no, a tornado, my cat's outside, I need to go get it. No, you don't. Okay? Cats can take care of themselves. You know, anyone say the worst thing to do in the weather emergency is be on the road. You can get kicked around, tossed around, things fall on you. You don't want to be on the road. Stay together. Because guess what? I'm going to be the last one out of here. And I'm going to take the roll with me. Because in the next class coming up, I have a guy who has a bad knee. He had an operation of his brain. And so if it happens in that class, I'm going to be with him, making sure he can safely, carefully get down the stairs. Okay, no one's going to push or panic or something like that. So I'm going to be the last one down there. I'll do the same thing here. I'm going to take the roll with me. I'm going to call the roll when we get down there. Okay? And if you're missing, and nobody knows where you are, that means I have to or someone has to come up and risk their life and health and be in external rooms when glass could start flying, limbs coming in the windows, and could rip. But we will try to find you. So don't leave. Don't get. After we call roll, then if you want to mingle with friends or find that dark room to go to sleep or whatever you can, but hang together to begin with. So there's the weather emergency. So we've covered fire or chemical spill or something like that. We've covered external emergencies like weather. What's the other one? Safety issue. Active shooter. Never used to even think about something as crazy as this, but nowadays you got to think. There's been one community college I've heard of in the U.S., and this was years ago, they had an active shooter, and several top universities have had them, and unfortunately many high schools, and you've heard about those, and then every place has had them, it seems like. So, what do we do? Now, number one, I'm hard of hearing. So if there's a pop, pop, pop going on, you're going to hear it before I will, unless it's really close, okay? So let me know, okay? And what do we do? If we hear the pop, 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 what do we do? Okay, that's ultimately where we're going to go. But actually, the first thing somebody called, and now, I heard something in the last class I hadn't heard before. If y'all heard there's a loss of state app you can get on your phone. Okay, there is a loss of state app. And they say when you pull it up, at the very top of the thing, I don't have my cell phone, so I can't show you anything. Very top of that is an emergency number, Birmingham campus, investment campus. So if you hear the pop, 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 someone call that number, because our campus police need to be the first to know. They probably probably hear it too, unless they're touring in some other building and didn't hear it, So that's one thing. If you don't have that number, the emergency number for our Washington Police, 911. Okay, that's next best. Best is, all right, they'll call 911, all right, the police will. They'll get all those balls rolling. They're the best to call. The second best would be that. Okay, so let somebody do that. Because I don't bring myself on the class. I don't want to have the distraction of it and stuff like that. So, someone do that. Now, here's what we've got to do next. This is a little bizarre. There is no way that I can lock this door from inside. There is no device. I don't know why every door doesn't have one of those little toggle switches that you can lock the deadbolt from inside. That's going to be my suggestion, what we do for safety purposes. Okay? So, can't do that. I can't even open the door and press a button here because there are no buttons. Okay? I have to go out. Unfortunately, I do have a key for this door. Okay? So I've got to go out here in the hallway and lock it from the outside and then come back in and pull it to. So I will take care of that. If y'all want to, you can be doing this, but if you don't, I'll do it. The bad news is there's another door to this room. And there's another door here. And there's a door there. And there's another classroom there. Okay? I don't have a key for that. And I'm pretty sure she's an adjunct. She doesn't have a key to that. So we'll probably get them to come in here, okay? And what we'll do is close that door, turn off the light, make it look like nobody's home. It won't be. Now, there is a door here, and it has buttons here. So it locks. Is that what we do? No. Why? It locks from the inside, but not from the outside. We don't want to lock ourselves in. We want to lock him out. Okay? Go with these other people. This would be even better. It has a deadbolt. I just don't have a key for that. So I can't. I will close this door. But then that door is just like this one. It has the button, so that locks from the outside, not from the inside. So that's the one we want to lock. Once we get those people in here, and that door closed, light turned off, that door locked, closed and locked. I'll close this door. I'll see there's a big window there. Easy for them to break the window, come on in, and get to it. So if this is closed, at least he thinks nobody's home. As far as he can tell, this door is locked. So I will do that. Okay? We're going to close this door, not lock it, because it locks us in. So we'll close this door. And then, as Clark said, once that phone call is made to campus police or 911, shut down the cell phones. You don't want them vibrating, you don't want them doing any noise. Okay? And we get back here, and we're as quiet as church mice, or something like that, whatever that is. Okay? And that way, this door is locked. He can see in, but he can't see back there. He can shoot through the door, maybe, there or here or something, but he can't hit anybody. It's sort of hard to shoot through concrete block walls, okay? Especially from being right here and shooting there. He's going to get more blowback than going to come through, okay? So hopefully he's not stupid enough to do that. But if it is, I hope we get him really bad. Never mind. But we're back here. We're as quiet as we can be until we get the word all this clear, okay? And we don't forget that. Now, if he makes it into the room through that somehow, don't be a hero. Y'all get behind things, cover, turn the desk, do whatever. Oh, I meant to tell you this one thing. Since I don't have a key to this door here, and it does open inwards, what I'm going to do when I'm back here closing everything, I'm going to take this table here and jam it up against this door and hopefully get it to jam against something else so no matter what, he can't get in. Even if he breaks the glass and reaches in, unlocks the door, if he knows enough to do that, he still can't get in. I thought of that last night, actually. I thought, no, I could do that, So, and I might need help with that, but I think I can get it done. We'll do everything we can to keep, out of here. And that's a tough door to deal with. So, and then we're quiet as door mice until we get Any questions on any area of safety? All right, good deal. I think we're through with that. All right, let's go to the calculus, maybe, finally. Okay. Now, this is Cal 2. Let me remind myself and you the first question, if anyone remembers in Cal 1 where we left off, and some of you from different schools and different classes and other things, do you remember where the last thing you covered in Cal 1? I know in my class we were in antiderivatives and integration, and we were doing definite and indefinite integrals. So I think we got most of chapter 4 covered, okay? But we didn't get into chapter 5. Chapter 5 is logarithmic, exponential, and other transcendental functions. And it's just sort of a quick go through. I think we can hit any, I think we've already hit in the earlier stuff, most of the stuff we need to know about that. But the question is, where do you feel like you need to start? Technically, to me, logistically, we start, according to the course description, 7.1. Do any of you feel like you need to review something before 7.1? Now, chapter 6 is differential equations. That's a whole another course. So don't worry about chapter 6. But is there anyone that needs to start somewhere earlier than 7.1? Let me know. Anybody? Okay, silence means assent. So is 7.1 it is, or do you have, I don't know where some of you are coming from. Some of you, I know where you're coming from. You were started the other course before, so we started 7.1 before, so that'll be even old hat to you. 7.1 okay? Okay. I wanted to know that before, so which one of these I need to open? All right. Now, as I was telling folks before, I was right at where we were before. Last time we got right up to integration by substitution, and we were just beginning to talk about that. Does anyone need to have her to go over that? Because last summer, you do. Substitution, integration by substitution. You got that, or you'd like to have it? Okay, let's go back. I'm sorry, I'll end this. Okay, let's go back, and that's 4.5. It's right there. It's the last section in chapter 4.
I don't think I got that far, because the last note that I had
It's what?
Area from 4.2.
From 4.2.
Yeah.
Okay, do we want to go before 4.5? Back to 4.2.
Like finding the width.
Okay, and what?
That and lower approximation. That was the last note that I had from my last semester.
Okay. Do you feel comfortable with 4.2 and starting in 4.3, or you want to start in 4.2?
4.2.
In 4.2 or 4.3? I can't hear.
4.2.
4.2. Okay. Okay. Is that okay with everybody? For some of you, it'll be a little bit of review, but most of you sounded like you're okay with that. Let's go back up. For some reason, I'm having trouble getting this to do anything. I think it didn't like that I stopped that where it was. Let me see if I can. Oh. Let me try that. Okay. Whoa, I didn't mean that. Yes. Okay, just a second. I'm sorry?
You know, we're supposed to be teaching this Math 100. It's got Bryant's name on it.
Okay.
There's no one here.
Okay, and where is that next door?
Right next door.
Okay, there was somebody in there. I thought that was a different class. Okay. It could be the doctor. First weeks are so much fun. We had the dean changed instructors in the class across the other next door, and I think she forgot to tell the new instructor, so they had a class of about 20 students or so sitting in there. The teacher from the first period class was still in there shutting things down, and they just thought she'll start teaching soon, and she shut everything down and left because she's not a math teacher. He knows that she was, I can't remember what, psychology maybe or something like that. So then they were waiting, and then they noticed that, well, they thought it might be traffic. Because I had trouble getting in this morning because they shut down part of the interstate. So some of them maybe have had the same thing. Then after a while, they just started leaving. And 4 students stayed, and they contacted Ms. Chisholm. And, they also checked on the phone to see if there was any messages, and they found out the instructor had been changed. And that's what it was. Somebody changed the instructor and probably didn't tell the new instructor that he had a class full of students. Well, he didn't even know. So hopefully that'll be taken care of for next week. All right. Let's see. Where do we say 4-2? Well, not there yet. There we are. Okay, so if it's okay, I'm going to try to go through this pretty quickly. I don't do anything very quickly, but I'll do my best to move it along because we're really supposed to start at 7-1. So let's do what we can. here. Okay. Where was your last note? Okay. Give me a page number or a example number or something like that.
Page 259.
To what?
259.
Oh, 259. Okay, I wasn't back far enough. Okay. Okay. Let's find that then. Whoops. Okay. Okay, you had done example 1. Had you done sigma notation?
Yes, sir.
Okay. This part of sigma notation? This is more sigma notation. You had done that? Okay. And then example 2, had you done example 2? That's on 259. You see example 2? Huh?
Yes, I got that.
You got that one. Okay. Did you get the answer to that? This is the bottom of 259.
Can we start with example 2 then?
Start with example 2? Okay. We'll go back and start with example 2. Well, actually, sorry. Let me go on and hit this 2. Okay, we'll start here. All right. We finally determined that. Then we'll start the slideshow at current slide. We've got recording going. All right. Now, some of you have already had this, so for you to review, but this is sigma notation. Well, this is a theorem that shows some of these summation formulas that we will be using later in example 2 and other places, so I wanted to go over these. If you have the sum of a constant from I to n, okay, does everybody know what that means? Are you familiar enough with sigma notation to know what I'm talking about? Everybody? Yes? Yes or no? Okay, yeah. Then, guess what? If you're summing up C from I to n, that means that C plus C plus C plus C plus C plus C. See, this is the first C. I equal 1. Here's the second C, third C, fourth C, fifth C. Somewhere out here is the NC, right? Going to N. Okay, so what is it? C plus C plus C plus C plus C. It's NC's, right? So what is that? N times C. Okay? So that's why it's C times N. Where C is whatever constant is in here, and N is whatever the limit of this is. You're counting by the integers, starting with 1, so it's C times N. So that's pretty straightforward. Now, we did this one in my class before. The summation from I is equal to 1 to n. That would be 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 up to n, whatever n is. Well, I sure don't want to add all those together if there's a lot of them. And I think I gave the example before. And just to fill in the blank here, let me get my pen activated. Okay. Give me an n. Pick an n. Any n in the world. 4. Okay. So that would be, this one would then be 1 plus 2 plus 3 plus 4. Okay. Now I can add those in my head and I know the answer. But if that was a really long number, here's what I would do. I would do 1 plus 4, 2 plus 3. And besides the smiley face, what have we got? We've got 5 plus 5 is 10. Now you can add those even easier than that. But any list, however long it is, start the highest and just keep adding in, and it's 5 plus 5. Okay? So our n, remember, was 4. Okay? And that would be I don't want to take too much time to do this, but that winds up still being the same as this. 4 times 5, 20, divided by 2 is 10. same as we got there, and basically what you're doing is half, okay, half of your n, half of 4 is 2, times n plus 1, okay? And that's exactly what we did. Half of the n was 4, so 2 times 5. That's exactly what we did. Half of 4 is 2 times n plus 1 is 5. Okay? And that will work no matter what your n is, every time. Okay. Now, what if it's I squared? I'm not going to tell you how to derive that, but this is the formula for that. Anytime you're doing a summation of an I squared, I going from 1 to n, it comes out that way. Amazing. I cubed comes out this way. These are just these summation formulas. Mark them in your book or something, you know. If you need one of these, go back and pull up this on page 259, and you've got those. So, now we'll start with example 2. How are we going to do this? Summation of I equal 1 to, okay, let me go back one more. This one. Here are 2 rules about summations. If you have a constant times an index that's being summed, pull the constant outside and just the sum of the thing being summed. Because this constant is just going to be summed every time. Well, let's just add them all together and then sum. It's easy. And if you have a summation of a sum or a difference, break those into the sum or the difference of the summations. Okay? Okay, so those 2 rules also. All right, now let's go to example 2. So here we have the summation from I equal 1 to n of I plus 1 over n squared. And let's do it for n equal 10, 100, 1,000, and 10,000. Now we want to write out all those terms? Please say no. Okay. All right. Whoa. Made an agreement and then forgot to tell anybody about the agreement. Okay. Okay. So what do we do with this? Any ideas? Second? Plug it in? Actually, not a bad idea, but before you plug it in, let's do a little bookkeeping first. Let's first change this sum to a sum of, okay, I'm going to write this first and you tell me if you agree with me. I equal 1 to n of 1 over n squared, I over n squared plus 1 over n squared. Huh? Same thing, isn't it? Now we have a sum, so isn't that the same as the summation from I equal 1 to n of I over n squared plus the summation from I equal 1 to n of 1 over n squared. He looked so similar, I thought, I just wrote that. No. Okay. Now, time out. Your summation is summing your i's, right? That's what's changing. The n doesn't change. Once you put n equal 10, it's 10. And that's where the plug it in comes from, right? So let's pull that on the outside. That's just like the constant. So this is the same as 1 over, we're going to start it with 10, so that would be 1 over 100 times the summation I equal 1 to n of I plus 1 over 100 times the summation of from I equal 1. Oh, wait, I'm sorry. The n, we're plugging in the 10. Okay. n equal 10. Sorry, I can't talk. 10, and this is 10, right? And that's just of 1. All right? What's that again? Yeah, because the n is 10. So I pulled it.
You already squared it.
I'm sorry?
You already squared it.
Yeah, I already squared. N squared. You see what? I'm sorry. We're doing n equal 10, the first one there. And the 1 over n squared comes out. That's 1 over 10 squared is 100. And then you do a 10. Okay. Now we know what this is, don't we? Look up the page. Okay. That zero. We know what that is. Right? That's 1 over 100. And what is the summation from, that's that number 2 up there. Summation of I equal 1 to n of I. That is n, which in this case is 10, times 10 plus 1, right? Divided by 2. You see that? Okay, wait. Okay. I take it some of you don't have books. Right here. The summation from I equal 1 to 10 of I. That would be 10 times 10 plus 1, which is 11, divided by 2. Just like we did before. That is what summation of that is. Okay? Whoops, went back the wrong way. What's that? Okay. Okay, we first did this. We said this is this. Okay, you see that stuff, right? Now, the next, okay. Whenever you have a summation of a sum or a difference, then you have the summation of the sum or the difference of those summations. So I split the I plus 1 and put summation of I and summation of 1. Okay? Okay? You were here this summer when we did this, you know? Okay. All right. So you see where I've got that? How that happened? Yay or nay? Okay. So we just plugged in what this is, and we got that. And we also have a 1 over 100 times the summation. And I think we can do this one, can't we? The summation of 1 from I to n, is it that? 1 plus 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 1. That's 10. N times 1. So this is 10. Okay? Well, all right. So let's do the math here. 5 times 11 would be 55 divided by 100. That's 55 over 100 plus 1 over 10. This would be 11 over 20 plus 1 over 10, which would be 2 over 20. That would be 13 over 20. Right? Sorry, my writing stinks, but I did it sort of fast. See how that works? Wait. You sure? No. Okay. Where did I lose you? Huh? Okay. Okay. Where is it? This? Right there. Okay, well, then it's up here. Okay, you got this one, but you don't have this one. Okay, what I did, because you see you're summing.
Sorry to interrupt now.
No problem.
But what you said it was, labs on?
What's that?
What room are those labs?
Labs, that's, it's 209A,
Yeah.
which you go all the way down this long hallway, take a left, go right past the stairwell, first door on the left.
All right, got it. Look at that. Sorry.
Okay. All right. So you got from here to here, right? Okay. Now, we're summing the i's. The n is fixed. It's 10 in the first case. It's 10. So we don't need to be summing all those hundreds in the denominator. Just pull that out. So we pulled out the 1 over n squared here. We pull out 1 over n squared there. Okay? And that's what that became. We're summing now just the i's. Well, all we got left here is just 1. Okay? Is that right? Okay? Okay, good. And then this becomes this, and this becomes that. This becomes n times 1, which is 10 times 1. Okay?
Is that a 100 right there, or is that 120?
What, this one
Yes, sir.
or this one?
That's a 100.
This one?
Processes. Yeah.
That's 100 because same as that, 1 over n squared.
Right.
I just pulled the 1 over n squared out. Okay? And then I did the math in my head. I hope I'm close to it. Everybody follow that? Okay? Let's see what the book, well, all right, for me to erase this, you probably say, please do. It's really ugly. We'll see how the book did it. They probably did it in a slightly different order. So let's see. First thing they did was they pulled out the whole 1 over n squared. Because it wasn't being summed anyway, so pull that out. And then they had the summation of I plus 1 here. So and that probably makes a little more sense. And then they split this into 1 over n squared times summation of I plus summation of 1. Right? Then, since they knew what summation of I was and summation of n, they plugged in those values. So it's 1 over n squared times this plus that. Okay? From those that they're looking at. Now plug in the 10. Okay? And when you plug in the 10, hopefully they got, oh, they did something else to it too. I think it's just as easy to plug in the 10 here. But what they did, I'm not going to argue with them anywhere, but what they did here, they put this all over 2, so that would be an n times n plus 1 plus 2n over, no, that's not right. Let me slow down a moment here. Oh, let me erase it off. Okay, sorry. I'm trying to go too fast. No, I did it right. It's 1 over n squared times, let's make this 2n over 2, right? Right? Okay, so that gives you n times n plus 1 plus 2n over 2, right? Well, this would be 1 over n squared. Well, let's multiply this through. That would be n squared plus n plus 2n over 2. Well, that would be 1 over n squared times n squared plus 3n over 2. Okay? Well, guess what? We can factor out one of these n's. So that gives us n plus 3 over 2n. Let's see if that's what they got. Yes, n plus 3 over 2n. That's about as simple as you can reduce it to. Now let's plug in. N equal 10 would be 10 plus 3. Second? I'm sorry? They're about equal. I think this way may be a little quicker. this dealt with the ends only. And, okay, let's go back here. They did the step, they just left off the step they got next, I think. They left off the step how they got there. I showed you how they got there, okay? And then I factored out an n, and they didn't tell you what they did, but that's what they, well, yeah, they did too. So I just showed you the two steps they left out, but that's what they wound up with. So now we'll do n equal 10. There'll be 10 plus 3 over 20, which would be 13 over 20. Is that what we got a long time? Oh, I already erased it off. Yeah, 13 over 20. Okay, whoops. So now let's do n equal, what was the next one, 100? Right? That would be 103 over 200. Okay? Let's do n equal 1,000. Was that the next one? So that would be 1,003 over 2,000. Okay? And was the next one 10,000 or 100,000? 10,000. That'd be 10,003 over 30,000. Whoops. Okay? And that's what, let me just erase mine because it'll get in the way. And that's what they did in the table here. Only they changed it to decimals. Why? I don't know. But you can do it. Go back and do, I erase mine. So if you got those numbers down, do them and you'll get these values. Now, what this leads you to ask, is there a limit as n approaches infinity for that summation? The one we had at the very beginning. What does it look like it's going to? 0.5. Let's see if that works. Now, this isn't what the book is asking for, but let's do it. Let's go back to this form right here. Okay? I think, yeah. And let's do the summation of this. The limit of this as n is going to infinity. Well, you could write that, do the limit in front. This is the limit of n over 2n plus the limit as n is going to infinity of 3 over 2n, right? You just split that up into two pieces, right? Now, the limit of that is just what? 1 over 2, 0.5. And what's this limit? As n goes to infinity, 3 over 2n, as n gets very, very big, like a million, that would be 3 over 2 million, that would be 0.00003 somewhere out there, right? That's going to 0. So sure enough, the limit is 1/2, 0.5. Okay? Now that was a bit more than the problem did, but that's where we're heading on it. Okay? So is that all right? Move on from there? Okay. Now we hit area. All right. I remember talking about this in my class. In Euclidean geometry, the simplest type of a plane region is a rectangle. Okay? Fine with me. I would say simpler than that is a square, but they said a rectangle, which is fine. Okay? Although people often say that the formula for the area of a rectangle is base times the height. Area is equal to base times height, length times width, whatever you want to call it. It's actually more proper to say that is the definition of the area of a rectangle. Well, isn't that what they just said? Oh, you can either say it's the formula for the area of a rectangle, or you can say it is the area of a rectangle. Wow, what a picky choice of words. From that definition, you can develop formulas for the areas of many other plane regions. Okay? And here's what they mean. What if you have a triangle? Okay? And this is what we call an acute triangle. Because it's really cute, right? No, that's not what we call it. It means every angle in that triangle is an acute angle. Okay? If one them is greater than 90 degrees, it's called an obtuse triangle. This is an acute triangle. So we want the area of that triangle. Well, what do we do? Split that into two rectangles. Here's a rectangle, and there's a rectangle. Okay? Now, this rectangle is exactly twice the size of this here. You can just take this and flip it this way, and you double it, right? Whereas this, because that's a diagonal, flip that over there, and you've got another rectangle. Well, you're adding this rectangle to that rectangle. This is part of the base times the height times the other part of the base times the height. Well, that just adds to the base times the height. But this is twice the area, so take half of it, you got 1/2 the base times the height. And that's what the area of a triangle is, 1/2 the base times the height. So you get it from that rectangle. Okay? Now, what if you had a parallelogram? What is a parallelogram? That is a four-sided figure, and two sides, each pair of sides are parallel to each other, but not necessarily at right angles to each other. So it's a lot like a rectangle, but not. Well, you can draw a diagonal across that either way, but I would do it the short line like they did, and then you have two triangles, and you can do it. The triangles. What's the area of the triangle? 1/2 the base times the height. And so, since 1/2 the base times the height, that's 1/2 the base times the height. This is base times height. 5 base times height. And sure enough, that makes sense. Because if you did a perpendicular down here, that would be exactly like the perpendicular you get here, right? Just take this one and move it over here. The base is the same. Now it's height. It's not this length, but it's that height. So yeah, there you have the area of a parallelogram. How about a hexagon? Now this happens to be a regular hexagon. I can't say that any hexagon you could do this way, but regular hexagons you certainly can. Regular meaning all 6 of those sides are the same length, and therefore all 6 of the angles are the same size. So do that and do diagonals across here, and you get 6 triangles. They're all the same triangles. They're not equilateral triangles, but they're triangles, and then you can do 1/2 the base times the height plus 1/2 the base times the height. Well, guess what? 1/2 the base times this height, since these triangles are all the same, so that would be just base times height, and that would be 3 times the base times the height of the triangle, not the parallel. So you got that. Well, here's a polygon. Have y'all listened to the weather things when they have weather emergencies? They talk about the polygons. Well, this is a polygon. It's a multi-sided figure. This happens to be a pentagon, 1, 2, 3, 4, 5 sides, but it's not a regular pentagon like Washington, D.C., which is a 5-sided building, by the way. That's how they named it that. This is an irregular pentagon. But guess what? You can still break that into 3 triangles. And 1/2 the base times this height, 1/2 the base times that height, 1/2 the base times that height. They're different bases, obviously, and different heights, but you can still do it based on that rectangle. Why are they showing us all this? I don't know. It is interesting, but it has not much to do with calculus. But they like showing it to us. Finding the areas of these regions other than polygons is more difficult. What would be other than polygons? Anything with a curve in it. A circle, an ellipse, any shape other than straight sides, okay? Those are really tough, okay? The ancient Greeks were able to, oh, by the way, I forgot to mark Daniel here. Psychological here, I guess, okay. Perfect attendance, by the way, folks. Way to go, keep it going. We were perfect attendance last time, before we added you. Perfect attendance today since we added. Keep it going, folks. Okay. So the areas of regions other than polygons, more difficult for sure. The ancient Greeks were able to determine the formulas for the areas of some general regions principally those bounded by conics, and we haven't really talked about that. And I don't know if he came up with it, but Archimedes is the one I always associated with, the exhaustion method. The clearest description of this method given by Archimedes, essentially the method is a limiting process in which the area is squeezed between two polygons. You can calculate the area of every polygon, and so you pick two of them, okay? And here's what we do. The area of a circle, okay? That is not an easy thing to do. It's not a polygon, so you can't use that rectangle for that. But you can put they happen to put a hexagon inside the circle. That's called an inscribed hexagon inside the circle. And you can do the area of these, just like we did before, 1/2 base times height, so it would be 3 times half the base times the height. Of this height, that base, because they're all the same. That gives you something less than the area of the circle. Well, do a circumscribed pair of polygons. Same hexagon here. This time it tends on the outside. Okay, so this is always bigger than the area of the circle. And you can do these. You can calculate those, see what by the way, the height here is the radius of the circle, okay? And then the base, you have to figure out what that is, but it's all figurable. Not easy to figure, but you can do it. And you got this. That's always going to be bigger. Now, what I would have done would have said, take the inner one, find this area. Not easy, but you can do it. Find the outer one, do its area, average them together and say, that's going to be close enough to the area of the circle. Now, well, they wanted to be a little more precise than that. So then they did an inscribed dodecagon or something like that, 12-sided figure, which again is just triangles. You have the area of this, that's going to be less than the circle. Then do the circumscribed one, and that's going to be greater than the area of the circle. Take the average of that, and I'm happy with that. I'm not going to do any more, but that gives you a better area estimate of the area. You can keep doing this till the cows come home and get closer and closer and closer to the area of the circle, okay? And that's how they came up with an estimate for the number pi. Because pi times the diameter is the area of the, wait, that's not right. Pi r squared, okay. Pi r squared is the area of the circle, okay? So.
Their patience were great.
What's that?
I said their patience was great.
Was very great. That's why they call it the method of exhaustion. When they finally got tired of doing it anymore, they say, that's close enough, okay? I'm exhausted, I'm tired, I'm not going to do anymore, okay? So for each value of n, the area of the inscribed polygon is less than the area of the circle, and the area of the circumscribed polygon is greater than the area. Moreover, as n increases, the areas of both polygons become better and better approximations, and that's why I would say take an average and quit, okay, but whatever. So let's talk about the area of a plane region. It doesn't have to be a circle. This happens to be a parabola, but it's a curved figure, okay? So how do we estimate the area of that? Well, we know the function. Now, here's what you have to have here. Your function minus x squared plus 5, there's the function. It has to stay above the x-axis. It has to be always positive. Okay, and this is from 0 to 2, okay? 0 to 2. That's always positive. So we can estimate the area by first taking little rectangles that are inscribed inside that area, okay? And they said 0 to 2, they wanted 1, 2, 3, 4, 5 rectangles inside there. So it's 2 divided by 5. Each one is 2/5 in length. 2/5, 4/5, 6/5, 8/5, 3/5, which is 2. Okay? Well, you know the height here of the inscribed one is the value, plug in x equal 2/5. So 2/5 squared would be 4/25 negate that, negative 4/25 plus 5, which is 125/25. So yeah, you can calculate the area of this. You know this length is, the width here is 2/5. The height there is whatever I just said it was, 125 minus 4. 121/5. And then do the same one here, and here, and here, and here. You just calculate the height times the width. We know the width is 2/5. Okay? That area is going to be less than this. There's your error right there. A little bit here, more there, a lot there, a lot there. But you got it. Or you could circumscribe the area, take the left-hand end of this, and do this as the height. So that's going to be 5. So for x equals 0, that's 5. So 5 times 2/5 plus whatever that. And by the way, that's the same value you had here, so you don't have to redo a calculation. Just do that. What was it? 121 over whatever it was. Okay.
121.
Second.
121 fifths.
121 fifths. That was it. 121 fifths times it. Yeah, and that, by the way, this one here is the same as this here, and these are the same, and these are the same, and these are the same. So you already done 4 of those calculations already. You just got this one extra here and that one extra here. But anyway, this gives you an overestimate. You overestimate about that, and that. And then, guess what? Average 2, and you're pretty close. But they don't ever do that. Okay? That to me would get you closer. So how's a better way to get closer?
Smaller increments.
Smaller increments. That's rather than fifths, let's do tenths. And we'll do those. And we already got a lot of those values calculated. And we'll do those when it comes with. And that would be even closer. And you can circumscribe and get even closer. And you can do that through the method of exhaustion too, can't you? But if you let this get smaller and smaller and smaller until that's going to 0, that's a limit, isn't it? And it's a limit of the sum of areas. That's what we're doing with integration. Limit of the sum of areas. Okay? So the right endpoints of those 5 intervals are 2/5 I. Okay? They're going back to their summations here. So notice the first increment, 2/5 times 1 is 2/5. 2/5 I is equal to be 4/5. 2/5 I is 3 is 6/5. 8/5, 10/5. Every one of those. Okay? So there's 2/5 I, where I is 1, 2, 3, 4, and 5. Okay? The width of each rectangle is always 2/5 of that one we showed there. Always 2/5. The height is when you plug in that value time into your function. Okay? Okay. And what they're saying here, I was looking at this thinking they're ordered pairs. They're not. These are intervals. 0 to 2/5, you do that area. 0 to 2/5 to 4/5 that area. 4/5 to 6/5 that area. This one, that. So evaluate alpha at each of the endpoints. And notice when you do those, and then when you go to do the circumscribing, you'll have these. You only have to do one more. Okay, basically. Okay. So the sum of the areas of those 5 rectangles. The height. Oh man. The height was alpha of this thing. Okay. And the width was the 2/5. Okay? That's a little bizarre looking, but guess what? You plug this into the alpha. Remember, alpha is minus this squared plus 5. Okay? So just plug that function in there, and you got this. Well, now, this is a summation. Okay? And it's really not fair what they just did to you there. They should have shown a few more steps. That's the summation from I equal 1 to 5 of, let's first pull the minus sign out and the 2/5 out, and that would be, no, I'm sorry, it's not a 2/5. That's a, sorry. Let me clean up and start over. Okay. All right. That would be, pull out the minus sign, and that's 2/5 squared. So that would be 4/25 times the summation I equal 1 to 5 of I squared. Right?
What was the function, the original function?
Oh, the original function, the f of x is minus x squared plus 5. Got it? Is that right? Y'all remember? That's my memory. There it is, minus x squared plus 5. Okay. What's that?
That's where the minus sign came from there.
Yeah, that's where the minus sign came from. Okay. And then we do plus 5 times the summation of I equal 1 to 5 of 1. Okay? Now, this would be minus 4/25. And what was the summation of all that? Remember I squared? Somewhere back here. Say again? N times n plus, no, that was I squared. It was this one. N times n plus 1 times 2n plus 1 over 6. Okay. Oh, whoa. Where did I go? Oh, I was going the wrong way. Sorry. Hitting the wrong button. Now I've forgotten what I just said, but we'll get there. In a year or two, here we are. So that would be times, what was it? N times n plus 1. Okay. N plus 1 times 2n plus 1 over 6, right? Yeah, okay. That was that one. And we know what this is. That's 5, right? Okay. All right. Right here. See here? It's a minus a 2/5 I squared. So I pulled out the minus, because that's not being squared. The 2/5 is being squared, and that's just left being I squared. Right? So that's how that got there. So you did that, and you
So you squared it, you pulled it out.
yeah, and I put n's here, I should have been putting 5s here. Say again?
So you squared I, and you squared 2.
Yeah, when you square the I, you use the formula for I squared. Okay, but I should have put 5s in there because I knew what the n was. So that, I wasted a step there. That's minus 4/25 times 5 times 6 times 11. Is that right? I'm doing it in my head. And n is 5? Okay. Over 6 plus 5. I put equals there. That's a plus. Okay. Now, the good news is 5 will go into 25 5 times. The 6's cancel out. And that leaves us with a minus 44 over 5 plus 25 over 5. There's something seriously wrong with this picture. That's not going to be the answer. Where did I botch that up? I have a feeling it has to do with the minus sign, but I can't see how to avoid the minus sign. The 25, when we squared the 2/5 and pulled it outside, is that the 25?
The last 44, negative 44, 5 plus 25.
This is negative 4/25 here, and it's negative 4/25 there, right? Is that what you're asking?
What is the 25? 25 over 5?
The one on the very bottom.
Oh, down here. This is plus 5, and because this is over 5, I wanted that over 5. 5 is the same as 25 fifths. 5 times? 5?
25.
Oh! Wait a minute. Yeah. 5 is going to 25 5 times. Yeah. So 5 is the same as 25 over 5. I was trying to get everything in fifths. But still, there's a problem here, and I can't figure out why there's a problem here. I've just done it wrong. I don't know. They skipped the step and didn't show you how they got it, which I find is a pain in the neck. And I'm sorry, I can't figure out. Yeah, I don't want to take too much of class time. Their answer, I'm sure, is right, because ours can't be negative.
I think he was trying to change it to like terms and
You know what I did? Yeah, this is 25 here. Is that what you were asking? Because this is 5 times I equal 1 to 5, that's another 5, and 5 times 5 is 25. Now we've got the right answer, okay? Because 25 is the same as 125 over 5. Now, say that again. Okay. Do you agree?
On the last part.
He's just saying that like 125
Yeah.
over 5 is the same.
Yeah, I'm trying, since this has a 5 in the denominator, I needed that to have a 5 in the denominator. But it looks like to me I still have messed something up. I haven't done anything with my 2/5 here. Or did I pull it? I forgot to pull that out front too. So it's not just 4 25ths here. You also have this too. So I should have this as 8 1/25ths. Because I forgot that. I left that off entirely. Sorry about this. I'm really botching this problem up pretty badly, am I not? Don't answer that question. All this is times a 2/5. So all this, and this is a 25 here, is times a 2/5. So our answer here is going to be times another 2/5. So let's see what we've got here. When I subtract those, I get 81 fifths times 2/5. That would be 162 25ths. And that's the answer they got in the book. Yeah, so that's correct. I forgot my 2/5 on the outside. I was just focusing on this part. Okay, the negative sign got taken care of here. This was 125 of this. When you subtract 44 from 125, you get 81 fifths. And multiply by 2/5, and you get 162. So we got it. They were right. I knew mine couldn't be a negative answer because they were positive things. And frankly, this is really tedious. And guess what? You'll never do this again. Okay, so don't sweat this. Get it, do it enough to get through it. Okay, but what happens if we use the left endpoint? That was which was that, the right endpoint? So that's going to give us a certain value, and they give you the decimal number 6.48. Everybody get that? Okay. If you do the other end of it, okay, and so there's our answer. You got it. It's in the book. You know, we're okay with it. Write it down. Let me erase all that and do the next one. Because each of the 5 rectangles lies inside, this is the lower limit. Now let's do it the left endpoints. That is 2/5 times I minus 1. See, the previous one was 2/5 I. Now it's going to be 2/5 times I minus 1. Okay? So that's the left endpoints. So your product is going to be this times 2/5, right? That's what I forgot to do before. we're summing all those. No, okay, that's not right either. This isn't a rectangle, okay. This is just the left endpoint, okay. The width of that is still 2/5, so we're going to multiply by that, but now your F is evaluated at this thing. Now, why they did it this way, I'm not absolutely sure. It works all right, but why didn't they just factor out a 2/5 rather than multiply? Well, no. I guess I see why they did. I still wouldn't have done it this way, but it's okay. They went on and multiplied 2I minus 2 over 5. This is the thing they're squaring and doing that to. See, frankly, I would have left it to 2/5, squared the 2/5, pulled it on the outside like we did before. They're doing it a little bit longer. And then they skip all the steps and say that's their answer. Okay? You want me to put the steps in, or do you know how they do that already? Put the steps in. Let's do it. Okay? Is everybody okay how they did this to be your endpoint? Okay. And this is F of that, and that would be F is this thing squared plus 5. Okay?
What's squared?
That was from our function. Yeah, the F is equal to minus x squared plus 5. Yeah, that's where that came from. So, this is what we're evaluating then. And it still bugs me to have that 2/5 over there. So here's what I'm going to do. From this step here, I'm going to pull that 2/5 on the outside anyway, because it's not part of the actual thing. That's going to be 2/5, the summation, I equal 1 to 5, of I'm trying to think the best way to do this. Okay. All right. That's going to be minus, I really don't like this, but I'll do it this way. 4I squared minus 8I plus 4. Just squaring that binomial. 4I squared minus 8I plus 4 over 25 plus 5. I already pulled the 2/5 out, so I don't have to fiddle with that anymore. Okay? Everybody okay with that part? Okay. Now, what that becomes is 2/5 times the summation, I equal 1 to 5 of, I'm going to change a little something here just to make it easier or clearer or mess it up or something. 2/5. Now, what I'm going to do is pull the minus 4 25ths out front and just leave an I squared. Okay? What I'm doing here is breaking this down, just doing this term here. Minus 4 25ths I squared. So pull the minus 4 25ths, that's a 5 there, it's really ugly. Summation of this, I squared. I don't know why that has to look so ugly. Let me see if I can make it cleaner. Okay. 25ths. Okay. And then the minus times the minus is going to be a plus. And that's going to be 8 25ths the summation of I equal 1 to 5 of I, follow that, plus 4/25 the summation of I equal 1 to 5 of 1, okay? Plus the summation, 5 times the summation I equal 1 to 5. That 5 there, it's just a pain. Okay. All right, this is going to be a 2/5 here, right? Times a minus 4/25 times, and then we have to plug in what this is. The I squared. Remember from before? Wasn't that n, right? 5 times 6 times 11. Wasn't it? Wasn't that what we had before? Over 6, wasn't it? I believe that's right. Okay? And then we're going to have a plus in that one. 8/20, okay. I'm not doing this well, okay? Okay. Okay. Let's put parentheses here and here, plus 8/25, and I, remind me what that one is, n times n plus 1, so that's 5 times 6 over 2, right? Plus 4/25 times 5, plus 25, because 5 times 5. All right. Don't you love it how they skip all these steps? Say, oh, it goes from here to here. You know, this is how you get to it, okay? Now here, this 5 can cancel into that and leave you 5. The 6's cancel out, and this gives you, and I just don't have enough room to write. Let's see if I can write it down here. 2/5 times, and that's going to be a minus 4/44 over 5. We had that before, right? Plus, I can't read my writing too well. This 2 will go into 8 4 times, and the 5 and the 25, that would be 5 times, and that gives you 24 over 5. Plus, 5 will go into 25 5 times, that would be 4 over 5. Oops, I closed it too soon. Plus 25. And I'm going to put it 125 over 5 again. Yeah. Okay. Are we out of time? I'm sorry. Let's add them up and see what we get. 125, if anyone got this, 125 plus 24 is 149, plus 4 is 153, minus 44, that's 1,
13.
say it again?
13.
Okay, and that's divided by 5, and then multiply that by 2/5, and do you get 202 over 25? I hope so, but if not, we're going to leave it there. I'm sorry. What did you say, 125 minus 28, that would be okay. That's 150. 3 minus 44 is, what did you say that was? 97? No. I don't know. The head's hurting too much. I can't do it. But anyway, supposedly it gets, if we did the math right, which we may not have, it gets 222. You get 8.08. Last time we got 6.48. Something in between the two. Okay? Now, because the parabolic region lies between that, you know it's in between those, between 6.48 and 8.08. What I would do is add them together, average them, and that would be my first guess. Okay? Now, we'll pick up next time with finding the area by limit definition. And believe it or not, I think you'll find this is easier. Okay. Okay. And then what we'll do is get into, that's right. It's still in 7.1. I mean 4.2. We're going to finish 4.2, and I'll try to go a little bit faster. Sorry about that, folks. And we'll go from there. We'll finish 4.2 and try to move a little more quickly through 4.3. No, 4.3 we can't go quickly. We'll do it as quickly as we can. And then we'll get the fundamental theorem of calculus, which is pretty nice. It makes it so much easier to do all this mess. And then we'll do the second version of that, and then we'll get into integration by substitution. So we've got a little bit of stuff to do. I'm sorry I took so long. These things are so tedious to do. It's just a pain in the neck. As soon as you learn how to integrate, it's so easy. So I don't see why spend all this time with the little trivial, tedious part when once you do the integral, it's so much simpler. In fact, we could have done that one, and I told you exactly what the answer was in about 5 minutes. Okay, so, but they're just wanting you to get the concepts down. Okay, and they spend way too much focus on that. So anyway, we'll pick up here next time. Any questions? And we'll try to move a little more quickly than we did today. Okay.